get started, what are actually variant-rich systems? A lot of people in software engineering work on this, and I think it's a common motivation. Typically, organizations, companies with whom we collaborate, with whom everybody else collaborates, start with developing one individual product. They have a really innovative product, a startup product, whatever, and they basically have this one system that they constantly evolve to meet customer requirements, and they have this one really successful thing, for example, here, a robotics arm. However, when they are really successful, new customers will come and they say like, yeah, we would like to have that, but a bit different. So they have individual requirements. And for that reason, a lot of modern systems from most organizations are just variant-rich systems. So for example, you have different iterations of robotics arms here, you have different types of camera systems, different types of information systems, the Linux kernel as one of the most prominent examples potentially. However, most organizations really start with clone and own, or cloning in general. And that means they take the existing system that they have that is successful, create a copy, and adapt this copy to new customer requirements. And then they have basically 2 or more individual copies of this one system, different variants. And this is really easy to use. It's readily available. Just copying a system, it's easy. Then adapting it, yeah, that takes more effort. So this has a lot of benefits in terms of it's really fast to use, it's really cost efficient in the beginning. However, over time, experiences mostly show that the increasing number of really independent variants drastically causes maintenance problems later on. And I mean, you can imagine that those are, for example, different forks in, for example, GitHub. And at some point, you potentially want to synchronize something between those forks or between your clone variants. So let's say someone introduced a new feature in their fork, and you are, this feature is actually interesting to other customers too. And now you want to synchronize this. Or you want to synchronize just performance updates. You want to synchronize, for example, the most potentially relevant thing, bug fixes. And here you have the problem how to actually do this for, let's say, 100 different variants. So just take a bug. You know that there's a bug in your variant, and then as in this example, you cloned and you synchronized with different variants, and the bug now exists in dozens of other variants. However, you are not even sure if it's the same bug because you changed something those variants too. Maybe that impacts the bug, or the bug impacts some new features or something else. So you have a lot of synchronization problems. This change propagation gets really expensive, and you lose an overview understanding of what is your software, what are your different variants, which also complicates like the starting point, selecting which variant you want to start your development with. And that has been shown over and over again in recent years. Those are really big problems. And in general, we can say that then companies start with re-engineering their variant-rich systems, and we can distinguish between different types here. So clone and own as the most simple one. Then you can introduce clone management frameworks that help you with synchronizing between clones. Then you can go to software product line or even a software ecosystem, just to name a few. Fundamentally, however, for our research, we distinguish between cloning on the one hand and platform engineering on the other hand. Cloning is just what I described. You have individual variants that are separated from each other. You somehow need to synchronize. A platform tries to facilitate this whole process by having one integrated platform with all your software features that you can configure and automatically derive individual variants from this one single platform. And yeah, some experience reports, some insights support that this platform engineering is more beneficial than having clone and own. So as an example here, it saved $340 million over 8 years. The development cost for a new variant, depending on its extent, can be like 5 to 10% of the previous development costs. So those are estimates, those are some reported numbers. But also there are considerable problems, and it's really risky to actually initiate this re-engineering. So for example, here it costed $3.5 million of investment. So you don't even have a payoff. You just invest $3.5 million to re-engineer the platform without having any benefit at that point. Other experience reports like Danforth's report, they planned for a 2-year program, and after 3 years, they were not even done with the code base. So it's really challenging, it's really risky. And the key problem that we have here is that we are building a lot of research and also a lot of practices on assumptions, on some hypotheses, on some educated guesses, like those individual case studies. Like, yeah, someone told us after 3 variants, the platform is more beneficial. We assume to have 3 variants, so we just do platform right away. So we have a lot of uncertainty actually involved in those processes, which again causes all those risks. And what we wanted to tackle, or what I want to tackle in my dissertation, is that I want to elicit a more reliable database for this, so that we have a lot of new and verified knowledge on all those assumptions, on helping practitioners better scope their projects, better conduct their projects, manage how they do it, and researchers in guiding, okay, where potentially are some misconceptions and where do we potentially need to focus on more, or where did we go potentially in the wrong direction. And current research really highlights 4 different objectives that in my dissertation, again, we found that they are really closely connected. And the first one is a really challenging thing that is open for like 3 decades now, that we really understand what are the actual economics of variant-rich systems. So when is it more beneficial to have clone and own? When is it more beneficial to have a platform? At what point in time should we re-engineer? And what are the costs? What are the investments we have with that? Because you need this to plan and assign developers to tasks. Then I will focus on the most important cost factor we actually found, that's the knowledge of the developers about your whole systems, about the variants. And one particular technique, namely feature traceability, to enable the documentation and facilitate the program comprehension of your systems. And later, as a last component, I synthesize all the insights we obtained before, particularly on practices and on activities, on the costs and how to do all of that into some re-engineering practices and the process model. But first, I want to start with the economics, obviously. And for that, just have a brief overview of our methodology for this one study. So we did this in collaboration with Axis AB, a large company of camera provider. Also has a lot of other systems. We mainly were concerned with the department on cameras. And we conducted interviews with 28 developers there, some exploratory, some for defining the process they employ, and some for the actual costs. So we basically scoped our study, defined activities, and defined some costs from the perspective of Axis. Obviously, the problem here is that's one single company. So we extended this by conducting a literature review and involving 58 additional publications. And that is data of more than 100 different organizations. And the good thing is they all hinted in the same directions. So we have a good confidence that this is actually something insightful. And in all those publications, we basically extracted like single data points. Like I mentioned, now we have 10% less bugs. Okay, takes this one data point. So it was really effortful to actually collect this data. And here, just to show you a brief overview, some snapshots. On the left side, we can now see what we have for Axis. They have different development phases, like designing a new variant, planning the implementation, and then implementing the new variant. And you can see here, yeah, not surprisingly, implementing the variant is most expensive. Whether you use cloning or platform, doesn't matter. However, we can also see that designing the new feature is more expensive in a platform on average. Those are the black bullets. And also the discrepancy, like the deviation from this average in design and in the actual implementation, is far bigger for platform engineering. And this is somewhat intuitive and confirmed by the literature. So for example, here we find 5 studies that indicate developing a new feature is considerably more expensive. And that's a typical assumption in software engineering. However, you really benefit from developing new variants because that gets much cheaper. And this can be really easily explained with some of our interviews. Basically, a new feature in a platform, you have to design it for reuse, for the platform, for feature interactions and all of that. And in a clone and own, you can just ignore it if you want to, until you have to synchronize, which causes most of the maintenance problems. So this study mainly resulted in a lot of confirmed assumptions on software reuse that previously were really based on educated guesses, a single case study that you found somewhere. And we really provide an extensive data set on those costs and cost factors. But also we found some insights that really challenged established assumptions in software engineering. So for example, that propagating bug fixes is more expensive than cloning. That's a really typical assumption. Our data actually indicates that it's more expensive and more problematic in platforms. So there's some really interesting insights. And as said, we confirm some assumptions, we also refute some, which is important. And also, we had again and again discussions with different companies, Starfinance, Grundfos, and so on. Some are using our data and they all say, yeah, it's really nice to know plan our project and it's going in the right directions. Obviously, it's not 100% useful for estimating costs, but it gives a really good indication. So this is basically comparing the development processes, but because we focus on re-engineering and when you decide to adopt a platform, you have to re-engineer. We also conducted 5 case studies. So we have a multi-case study on re-engineering. I don't want to go into the details of the methodology, just a brief summary of the benefits. So when you re-engineer your cloned systems towards a platform, you can immediately develop new variants. You can improve your code quality. You have a better management of the variability, so of which features you can configure and which you cannot configure. And you can remove unused code and reduce your code base. So those are typical benefits that we also found again and again in those case studies, also with practitioners, with industry. So that's really good. On the other hand, we also confirmed quite some of the challenges that have been sometimes indicated. So for example, the available tooling is still not ideal, mainly because it's not scoped to the actual needs of the developers. So the research tools are nice, but they don't really support the actual reengineering because there's missing support for what developers actually need. And then we have deciding about features and intertwined activities, royalty mechanisms. All of that is related to how we actually implement it. And the most important thing we actually found is, as already motivated, developers' knowledge is basically key. They need to know what features exist, what code implements those features, which features do I need in the platform, how do I re-engineer them, how are the practices, how are the processes. And this is what we basically want to focus on. And one other thing, because we will come back to this again, we found also that virtual feature traces, so like annotations in the source code, are obviously or are far cheaper to introduce than having any other traceability mechanism, independent of variability in this case. So because we now found that knowledge is one of the most impactful, most expensive factors in re-engineering ground-rich systems, we basically investigated this property in more detail. And for this, we've conducted an interview with 17 developers, most of them actually from industry or academia industry collaborations. And we first want to understand what types of knowledge they actually perceive important when they work on their systems, and what types of knowledge do they not perceive important. And in general, we just clustered those into architectural knowledge. So what is the structure? What are the classes of the system? Into meta knowledge. What are the involved developers? Who's responsible? What are processes? And into code comprehension. And here we again distinguish between really high-level code. What is the intention of this code? So what is its general functionality, for example, versus really low-level code? What are parameters of a method? What is a bug in this code? And yeah, we covered various domains, different programming languages. Only remark I have to make is this was mostly on smaller systems. So most of them had less than 10,000 lines of code. We also had 4 or 5 that had above 100,000 lines of code. So it's not too challenging, but yeah, this is something we have to keep in mind. And most developers had 6 active, most systems had 6 active developers at a time, but some systems had like 50 plus developers over the whole process. But again, some smaller systems. Still really experienced developers. And here we can just see for all the questions, so we asked 6 questions per category, how important the developer thought this knowledge would be for them to work on the system again. And we can see architecture knowledge, most important by far. Then code knowledge, which is really interesting. We see this gap, right? The high-level code knowledge is perceived really important compared to architecture. What is the intention of the code? What are the features? Whereas the low code level, where we go more into the program comprehension part, into the actual I need to read the code to understand it, is perceived less important to just memorize, to keep it in memory. And meta knowledge, also perceived least important. Again, here is a comment. We had smaller systems with fewer developers, so that may bias those results. However, again, the importance was validated. We designed this whole study on a literature review of related studies, and they hint in the same direction. So we're actually quite confident that the results are still reliable. And yeah, particularly this pattern was really interesting. Again, high level versus low level on code level. And now we actually reiterated through all the questions and checked with the developers whether they answered the question correctly. So they had to answer those questions, and then they had to rate how important they perceived them. And now we basically looked how often did they correctly answer the questions. And here we have a similar pattern in terms of they answered architecture questions most often correctly, code then meta. However, we can also see that they are really good in general. But correctness, again, aligns with importance. And we see, again, the pattern for the code level. High level, more important than low level. So again, as an insight, developers are really good at remembering knowledge about the system, particularly high-level knowledge. For detailed code knowledge, they're actually not as reliable. They forgot it easier because they don't perceive it as important to remember because they have the source code to check it again. However, here we wanted to understand this in more detail, how they forget. And we adopted concepts from psychology, namely forgetting curves. And without going into details, we basically here asked them to assess how much they still remember about the file they worked on. So this is a different survey with 60 developers, roughly. And here we can basically see this blue line is the average of the responses, and each circle is basically one response. And the larger the circle, the more often the developer worked on the file we asked them about. So a large circle means they edited, committed to the file 100 times. The small ones mean they edited it once. And we can see the day since the last commit. And in psychology, we would assume that this exponential decline we see in the beginning would just continue. And we can obviously see that's not the case here. So something else has an impact. And those circles already hinted it, and we investigated different factors. The first one was the file size, so that large files wouldn't impact the memory, which it shouldn't, because we asked the questions to avoid this. And there we didn't find any significant correlation or any correlation, any even weak correlation at all, so that's good. And then the circles actually indicated the number of edits the developers did, so the repetition. And here we found actually moderate to strong correlation. So repeatedly working on this, as we know from learning theory, impacted and improved developers' memory. The same we found for whether you wrote the code yourself or whether the developer just worked on the code of someone else. For tracking, so code reviewing and so on, we didn't find any correlation, but maybe due to our questions. So in general, as said, like for identifying who is really knowledgeable and when they need what support, so for example, at what point do they need really code comprehension support, we had some really interesting insights here. And particularly, you can rely on the developers that repeatedly worked on the code to actually understand what it does. So because this code comprehension is a problem, particularly if you want to, for example, to onboard new developers, or you have a larger team or a changing team, we considered now feature traces. And feature traces are really established concepts and are typically combined with configurability. So on the right side here, you have an example with a C preprocessor. And the feature traceability is basically this if defining that the feature Unix is implemented in the next line until the else. So this is a straightforward, easy example, actually not too complicated. However, this is really complicated. It has like one if def, it has one complicated if directive where it's not clear what feature that is. And all of this is basically one statement. It's only one if. So this can get really complicated to understand what features are implemented if you combine it with configurability. And to understand this in more detail, we conducted 2 experiments to understand how to design feature traces. And here, as the results for the first experiment, we just compared feature comprehension versus bug localizations for annotations, so comments in the code, versus having separate files for the different features. And here we found that apparently feature traces improve feature comprehension, particularly interaction comprehension. They seem to improve it. And we found that this is true for annotations, at least in 2 of our cases. As you can see, if we have no traces, which is the n, on the right side it's always the one with the lowest numbers of correct answers in our experiment. On the other hand, for bug localization, yeah, we didn't find this trend. We can see here that physical separations to separate files seem to be worse than no traces. And we also confirmed this for at least one case. So our general insights here were that we should focus on virtual representation. And in this experiment, we conducted a study with 560 developers. And without going into details, the important thing is task 1 was on code comprehension. Task 2 was on configurability comprehension. So can they understand those configurable annotations? And we can see here in general, all developers considerably performed worse on the configurability understandability. So they could understand the code, but not really well the configurability of the system. So that is how we decided or defined, yeah, you actually need some feature annotations that should not be configurable in your platform or in your cloned systems, so that you can really trace the knowledge of the developers, not necessarily how the system is configured. And finally, to synthesize everything into practices, I want to give a really brief rewind. Those are typical platform engineering processes. You first design the platform, then the variants. Problem here is you have a strict separation between both phases. You have evolution only through the platform, and you have only proactive adoption, so only platform adoption. In our previous studies, we found that this is not how this happens. And we conducted basically literature review again. We relied on our experiences with collaborating with practitioners, and we extract a lot of activities from the papers, from our interviews, and designed this promote PL process model. No worries, it's much more detailed in the granularities. I don't want to go into this, just as a brief summary. So we switch from this platform versus variant development to adoption versus evolution, which is predominant in practice and more interested to practitioners. We included different adoption strategies, namely adopting a platform, adopting cloned own towards a platform, re-engineering. And we have particularly this variant-based platform evolution finally integrated into this process model. And for the actual planning of the process, for the supporting practitioners, we have also derived feature modeling principles and guidelines for assessing where you are in your re-engineering project. So to give a final conclusion on all of those changes that we have here and all the insights of the dissertation, we try to improve on those assumptions, and we first elicit a huge data set of economic data, helping developers to justify their decisions and managers and plan their projects. We understand how developers' knowledge needs are during the re-engineering and how to actually help them regain it. Then we recommended how to implement feature traces to improve this knowledge and then facilitate costs. And we finally synthesized everything into a new process model and some recommendations for practitioners how to re-engineer their variant-rich systems. And with that, I would like to thank you for your attention. And if you have any questions, feel free to ask.